what I'd like to do today is to try to review really old results, but from a perspective that, at least for me, is a bit new, kind of trying to unify research really over decades. So in 1970, we had a very important paper was published by Ted Cott, which is the beginning of relational database theory. And there was a point of departure there, because when I learned mathematical logic, the focus was on sentences. Sentences either true or false in a graph, and that enabled us to define classes of graphs, of structures, structures or graphs for particular. And because that means that logic, a sentence or a theory define a class of structure, logic provides a meta theory for mathematical modeling. And this is what model theory is about. Now, what Ted Cott has done is take a concept that exists in mathematical logic, but was a more narrow technical notion of definability by formula, but he promoted it to say, no, this is really important. Formulas are really the important object because they define query. When you apply a formula phi to a graph G, you get as an answer the set of tuples represent as satisfying assignments. Please mute yourself, I hear noise. So the set of tuples representing satisfying assignments over that graph is the answer to the query. So for example, if I have the formula exist y and z, such that y is different than z, and there are edges from x to y, x to z, the query is give me all the nodes that have at least two distinct neighbors. Sentences are a special case that represent Boolean, yes, no queries. Now, implicit in Cott's paper, I don't even know that he's addressed, I don't remember if he explicitly mentioned that, but it's obvious that query evaluation is decidable over finite structures. So as we kind of discuss what is the beginning of finite model theory, I actually think that this paper never used the phrase finite model. I don't even know how much it used the word finite, but it is a milestone, a seminal paper in finite model theory, because this result on one hand is trivial, but at the same time it is profound. And here is what I mean by logical algorithmics. So typically we think about algorithmic, we think in the following way. If somebody gives you some kind of a property, colorability, reachability, and you go and you design an algorithm for this specific property that you want to know. Is the graph connected, okay? Things like cyclic, acyclic, things like that. The logical perspective is that we specify the property we're interested in by a sentence in some logic L. And the expectation is that this logic will be decidable on finite structures via a uniform algorithm. If you think about it, it's not just that we have that the semantics of first order logic is on finite structure is decidable. There is one algorithm that does it. So I call it the QE, query evaluation. It's not Queen Elizabeth, it's query evaluation algorithm. We evaluate phi on G, and it gives you, for at least for focusing on Boolean for simplicity, the answer is 1 if the sentence satisfies the formula. Now, when you start thinking from that point of view, it becomes very clear immediately that there are many interesting properties that cannot be expressed in first order logic. So when you come from the algorithmic perspective, first order logic is actually rather weak. Like colorability requires existential second order logic because I have to quantify over the colors. I have to say there exist color classes and so on and so forth. The rest is first order. So immediately first order logic also is being kind of demoted from being very special because it's clear it can only capture relatively simple properties. And that's kind of, out of this came a very important paper by Ron Feg in 1974 that looks exactly this existential second order logic. And it shows it captures precisely NP time. And in both directions, every property in NP can be described by existential second order and vice versa. And the reason this is an amazing result is because it does not explicitly mention computation. It does not explicitly mention polynomials. Nevertheless, we have this result characterizing NP using logic. And this is the beginning of descriptive complexity theory, where we were looking at not computational complexity theory, but the complexity of describing properties. And so descriptive complexity theory emerged as a more deeper investigation of this connection between computational complexity on one hand and the syntactic complexity of the logic required to express properties. For example, one easy consequence of Fagin theorem is the polynomial hierarchy is precisely the class of languages is expressible in full second order logic. And out of this came a deep investigation of the connection between computational descriptive complexity, and the book by Immerman in 1999 kind of put it as a major subject in between final model theory and computational complexity. Now let's go back to the meta algorithm, the uniform algorithm, the Curie evaluation algorithm. In 1982, I asked myself the question: what is the computational complexity of this algorithm? And you run into two issues. One, you say, well, it depends on what logic we're talking about. There is a difference between first order logic and essential second order logic, for example. But the other thing that I struggle with is what is usually we measure complexity with respect to the length of the input. How should we measure the length of the input? Because we have two parameters, two inputs variables, the query and the structure. What Fagin's theorem told us that for each fixed sentence in essential second order logic, the complexity of Curie evaluation is in NP for each fixed formula, for each fixed sentence. What happens if I consider also the query to be variable? And then the question is what logic to consider. So we already mentioned first order logic and essential second order logic. In 1971, Aaron Ullman showed that this was actually followed from earlier result by Fagin in his dissertation. Aaron Ullman showed the first order logic cannot express reachability. Because reachability, we need to know that there is a path of length 1 or 2 or 3 or 4 without a priori bound. So Aaron Ullman said you need first order logic with induction. And this first order logic with induction really ultimately converges to a logic which we call today fixed point logic, FP. And it is easy to show that first order logic is less expressive than fixed point logic, which is less expressive than essential second order logic. So we have at least 3 logics here to consider: FOL, FP, and ESO. Now going back to the question that we have 2 input variables, and the challenge is that, again, that standard complexity theory looks at resource use, time, memory, as a function of the input size. But here we have input size would be database size plus query size. And let's suppose the database size could be maybe a gigabyte, and the query maybe 100 characters. So in some sense, the query size, we say the query size has no impact here because it is such a small number. You know, clearly imagine the difference between doubling the database size or doubling the query size. It does not reflect well here. So the point is that the database size and the query size play a very, very important role. And this idea that you have different input variables with different roles is not reflected in standard complexity theory. So to do, if we want to deal with complexity theory for logical algorithmic, we have to separate the influence of data and the query. And so to separate it, we can fix the data and only study the query, or fix the query and only study the data. And there are real life applications that correspond to that. If you look what happened in the census, data is fixed for 10 years. United States by constitution would do a census every 10 years. And then the data is fixed. People run different queries on it. But let's suppose you're sitting on Wall Street, you're a quant on Wall Street doing price arbitrage. You may have a fixed query, but the data changes every minute. So you're running same query, different data. So this gives us 2 notions of complexity, a tale of 2 complexity, I call it. On one hand, you can fix the data and just look at the complexity with respect to the query. And we can call it query complexity, or sometimes I call it expression complexity, because also it depends very much on the syntax of the query. So this is one way to evaluate, to look at the complexity of query evaluation as a query complexity. Other one is we fix the query and we vary the data. And now we're looking at the complexity with respect to the data. So this is data complexity. And what I discovered in 1982 is that there is exponential gap between these 2 complexities. For example, first order logic, data complexity is log space, but query complexity is p-space complete. Look at fixed point logic, data complexity is polynomial time. In fact, it's p-time complete. Query complexity is exponential time complete. And essential second order logic, we saw NP complete, Fagin, but the query complexity is next time complete. So the theory here justified the intuition that the query has structure, very rich structure. The data is just flat. And in some sense, that explains why query optimization is so important, because this is the source of real difficulty, is the query. So let's see if we can optimize the query. And it turned out that this distinction with data and query has very broad applicability. It shows here in relational databases, it shows in many other, it shows in model checking, I'll come back to it, it shows in knowledge presentation. And in fact, out of this, what we call today multivariate complexity theory, which have multiple variables, a few years later came a parameterized complexity theory that also look at and today the new name is multivariate complexity theory, but even in parameterized complexity theory, we have different input variables. So now let's take a look again at the issue of descriptive complexity theory. So we show by Fagan theorem that data complexity was ES for ESO is NP time, and query complexity is next time. Now we can ask, okay, what's about the relationship between fixed point logic and P time? And Immerman and myself showed in 82 that over ordered structures, FP is equivalent to P time. Same way that Fagan gave us ESO equal to NP time, but there you did not need order because you can quantify over order essentially. You can say, let there be order, and poof, there is order. Okay, fiat order. But in fixed point logic, we can't generate the order, so we have to assume it. And it's major open question posed by Chan and Arel and Gurevich. What about P time over unordered structure? And it's still, as far as I know, wide open. Now, I want to take that lens and show that this lens also can be now applied to consent satisfaction problems. So in consent satisfaction problem, which is a major problem in AI, it's a branch of AI today. It says its own conference, consent programming. This is the fundamental combinatorial problem. You're given a finite set of variables. They range over a domain D of values. And you have a finite set of constraints. And a constraint is a tuple of variables in a relation of the same arity. And what you're looking for is a global assignment of the variables, of values to the variables, and such that each local consent is satisfied. So you look at every pair T, comma R, the image of T, H of T, has to be in the relation R. And the question is there such a global assignment? So we have local, we want to satisfy local consent, and one global assignment satisfies a bunch of local constraints. And you find this problem everywhere, in belief maintenance, machine vision, NLP, and so on and so forth. It's a very, very important problem. It covers a huge number of combinatorial decision and optimization problems in computer science. Now let's take a look at another problem that's not so well known, and this is the homomorphism problem. So here you have two structures, A and B, over the same vocabulary. And homomorphism is a mapping from the domain A to the domain of B. And the domain has to be such that every tuple in A is preserved. It's one direction. Every tuple A1 to AN, it's in the relation R sub I over A, if the image of the tuple is in the relation R sub I over B. So we have preservation in one direction. Strong homomorphism would give us if and only if. If the mapping is also but if it's a bijection, then it will become an isomorphism. So the decision problem is given to relational structure, is there such homomorphism from A to B? And a simple example is if the structure B is a 3-click, then we are really asking here it's exactly 3 colorability. Okay, if A is a graph, undirected graph, and B is a 3-click, it's really 3 colorability. And it turns out again, homomorphism, there are many, you can phrase many problems as a homomorphism K-click. You're asking, is there mapping from the K-click to your structure? Hamiltonian cycle, you can ask, is there a mapping from a cycle of the appropriate length into the structure, while we are forcing here, it must be 1-to-1 by adding the inequality relation that also must be preserved, and so on and so forth. Even ST connectivity can be expressed as a homomorphism problem. And in 1993, Thomas Feder and I argued that CSP is the homomorphism problem And what does it mean is, as Bill Clinton said, depends on the definition of is, but what we observe here is that the reductions between two problems are so trivial. This is really a syntactical transformation. We should not consider them a separate problem. It's just one, it's just the same problem, phrased somewhat differently. Now we can kind of go back and look at it from this logical algorithmic point of view. The uniform problem for CSP is given a pair of structure AB, the homomorphism from A to B. And it was first shown to be NP-complete by Leonid Levin in 1973, but we already saw that this is the three-colorability is a special case of this, so it's obviously it's NP-complete. But now I want to take the multivariate complexity view of you. I want you to think of A as the query and B as the data. So A is the pattern you're trying to identify, and B is the data, it's the database you're trying to say, does the pattern exist inside the database? And in fact, this can be expressed, this can also view as what we call conjunctive query, essential positive conjunctive first order logic. So this is the uniform case, but now we can do the data complexity by fixing the source. So the query A is now fixed. We are varying the data. The data is B. So we're looking all the structures B such a morphism from A to B. And because now the source A is fixed, and it's a special case of first order logic, this is going to be in log space. So the fixed source, the data complexity point of view here is not very interesting for a single query. What about the other one? Let's suppose that we fix the target. We vary the query, we vary the pattern, but we have a fixed data, a fixed target. Well, now you see that it depends on the target. Again, if we're just focusing on undirected graphs, if the target is K2, then this is two colorability, which is, we know, in polynomial time, in fact, in n-log space. But if the target is K3, this is three colorability, which is NP-complete. So we see that the data complexity very much depends on the target B. And this gives rise to an interesting research problem to try to understand, to try to classify. We have a large class of problems depending on the target. Can we identify the tractable cases for fixed target? And in some, this is a large subclass of NP. Can we somehow classify the difficulty of problem there? And in 1993, Feder and I conjectured there is a dichotomy. So either the target, for some targets, the problem is polynomial time, or it is NP-complete, and there is nothing in between. This is what's interesting. There's nothing, that the conjecture is nothing in between. And this, we can go back to Ladner, who showed that in general, if P is different than NP, then there are lots of in-between problems between NP and NP-complete and P-time. In between, they're in the space in between NP-complete and P-time. There are lots, it's very rich. It's a very rich space. There are lots of problems there. And the conjecture that for CSP, for homomorphism, we don't have it. They are just P-time and NP-complete. The evidence for the conjecture was first looking at earlier work. There was a paper, earlier work by Helen Neshetril. They look at undirected graphs. And if B is the target, they show that if B is bipartite, then this is really corresponds to two colorability, and therefore it's in P-time. But for every non-bipartite B, you can reduce it to three colorability, and therefore it's NP-complete. So again, you have a dichotomy depending whether B is bipartite or not bipartite. Another earlier dichotomy was looking at Boolean CSP, where the domain is just 0 and 1. And then we can capture all kind of satisfiability problem. For example, a 2-sat corresponds to having the three type of clauses, both positive, both negative, and one positive, one negative. And this is a particular type of a particular target B. And Schaeffer showed in 1978 that for Boolean domain, for target, Boolean target, either there are really a few cases that are tractable, which is the trivial case, all relations are empty or full. Horn, anti-horn, disjunctive, affine, and these are the cases it's in P-time, otherwise it's in NP-complete. And I won't go into tell you exactly what each class is, but the point again, you have a dichotomy. So this is, we're looking at the terrain of problem. Thomas and I tried to resolve the dichotomy conjecture, and we were not able to do it, but we were able to at least describe the terrain. On one hand, we show that there is a subclass of NP, which we call MMSNP, monadic monotone strict NP, which is a fragment of ESO, and it can be reduced to CSP. So if there is dichotomy, dichotomy will be already in MMSNP, but if you drop one of the condition, you drop monotonicity or you drop strictness, then it's equivalent to all of NP. On the other hand, the question was, we look at general structures, can we simplify this? And answer was, considering directed graphs is enough to settle the conjecture. Now, the other question is, what is the source of tractability? So we looked at the terrain of problems that we found in the literature, and all known, we observed that when you get tractability, it comes from two reasons. One is combinatorial, which correspond to consent propagation, and one is algebraic, essentially extension of Gaussian elimination. And again, we had another conjecture there that these are only two explanations, combinatorial and algebraic. So let's dig a little bit into the algebra. If you're given two graphs, you can take their product. The domain is a product of the two domains, and you take a product of the two edge relations by saying there is an edge in E1 cross E2 from UU prime to VV prime if the two corresponding edges exist. And this is standard notion. You can take it to relational structures as well, take the product of relations. And this gives rise to a notion of polymorphism. Polymorphism is a homomorphism from some power b to the k to b itself. And in '93, we called for the study of polymorphism. We didn't call it polymorphism because we didn't know about the term. The term was known, but we did not know about it. We call it a closure condition. But we showed the following. We showed that if the polymorphism of B contains a near unanimity function, what is near unanimity? If you have a tuple of variables, and at least k minus one of them equal to some A, then output is A. So it does not require that all k variables have the same value, just that k minus one of them have the same value, and that value should be the answer. So if polymorphism of B contains a near unanimity function, then you can solve the problem in polynomial time combinatorially by consent propagation. So we call it preservation properties, but this went on to be studied. And it turns out we did not know, but polymorphisms are a major topic in universal algebra. And following our 1993 paper, Gibbonson and his colleagues showed beautiful theorem that says if two targets B1 and B2 have the same sort of polymorphisms, then the corresponding CSP problems are polynomially equivalent. And that means that to study the complexity of CSP over a target B, we just need to study the polymorphisms. And that gave result to a research program of almost 25 years. And finally, in 2017, Andrei Bulatov and Zhuk independently at the same conference, Fox, proved that indeed the economic conjecture holds. In fact, it's more, it's even decidable. We have a decidable classification problem. It is given B, we can determine if it's polynomial time or if it's NP complete. And if it's polynomial time, we can determine whether it can be solved algebraically by the means of polymorphism or combinatorially. Now you think, okay, classification, the economic conjecture solved, end of story. But there is something which I call the semi-uniform. And what is a semi-uniform? So we saw that fixing the query is not very interesting because it just trivially log space. But what if instead of fixing the query, we have a class of queries? For which classes of queries is the query complexity tractable? And what the notion that we propose is to look at the core of the source. What is the core? The core of a graph, the core of a structure, is the unique minimal homomorphic substructure. And all minimal are unique because they're isomorphic to each other. So let's take the class C sub k to define the structure whose cores have 3 widths at most k. Just to remind you that every graph there are 3 decomposition. And if you look at the 3 decomposition of minimal width of nodes, that's the 3 widths. And in 2002, Dalmar, Colaitis, and myself showed that CSP of CK is tractable. This is a large class of queries for which we have tractability, and we use logical games to do it. The question is, can you do better than that? So we showed it required this, we have this island of tractability, but there are negative results that followed up. Grohe showed that under some complex theoretic assumption, FPT is different than W1, then CSP of A, some class A, is comma period is tractable if and only if A is contained in C sub k. So this gives us the C sub k is an upper bound under a complex theoretic assumption. And Atserias, Bulatov, and Dalmau showed that again the CSP of A, comma, everything is solvable combinatorially. We said algebraic and combinatorially if A is contained in CK. So CK is a large island of tractability, and most likely it seems that there is no larger class. So in conclusion, on one hand, on the CSP, we have a paradigmatic problem with deep connection across from computational complexity to graph theory to algebra and logic. But this is not the end of the story. For example, the 2021 Gödel Prize was given to 3 papers on CSP by Bulatov, who looked at the counting consensus satisfaction problem, and then Dyer and Risherby, who had effective dichotomy for counting CSP, and then to Tsai and Chen, who had the complexity of, again, dichotomy, but now with complex weight. So this is still, and one can look at also at a fine grain complexity, which I'm trying to understand below p time, when is it in n-log space, for example. So this is still much research to be done on this problem. And going back to our starting point, logical algorithmics, they give you a perspective on algorithms and complexity that binds together descriptive complexity theory and multivariate complexity theory, and we show the connection to CSP. And there is another important, very important applied connection to model checking, where again, you have a property in logic. In this case, usually people use temporal logic, and the structure is the program, and we're trying to, again, to evaluate properties over finite structures. And that's is subject for another talk. Thank you very much.